For the next section today, we'll be looking at an open cylinder filled to some level h naught with fluid, with a total height h, a total radius r. And we want to derive an expression for the total maximum frequency that the cylinder can be rotated without spilling any of the contents. So this could be really important in many real-world applications. One would be in chemical reactions. Many chemical reactions use stirring as a catalyst. And if you want to know the maximum frequency you can stir it with without spilling any, this would be very important to use. So first we can draw what this cylinder would look like being spun at some maximum frequency where it doesn't spill. So at the frequency that it doesn't spill, the top of the fluid will be right at the top of the vessel, and the bottom will have dropped to some level below h naught. And so the first thing we want to do is we want to derive an expression for the pressure at any point in this vessel. So let's choose this as just our point. So at this point we will have a radial pressure at some distance r, and we'll have a vertical pressure at that distance h from this level to the height of the fluid. So starting off, we will just start with basic equation of fluid dynamics, which is differential pressure over differential radius equal to rho times acceleration. And we also know that acceleration is equal to the angular frequency squared times the total radius. And so this is important because we want to derive an expression for the frequency, so we want to put that in there. So we'll just combine these two equations, giving us dp over dr is equal to rho omega squared r. And from here, we just want to separate this and then integrate. So we'll have dp is equal to rho omega squared r dr. And so for this p, it's very easy integration. We're going to go from p1 until p, and I'm going to make this a dummy variable of integration. And for the r, we're going to go from r1 to little r, and that r would be any radius in this cylinder. So you could find the pressure at any radius in this cylinder. So quickly integrate this. Well, first, this would be the point of our P1, R1, which would make both of those 0. So the pressure is right on the surface of the fluid, so it wouldn't have any pressure from the fluid, and the radius is obviously 0 because it's on the center of the cylinder. So this makes this a really easy integration. On the left side, we have P minus 0 is equal to rho omega squared. Those are both constants, so those stay on the integral. And that'll be over 2 from r minus 0, r squared. So this will give us a final equation of the pressure is equal to the density times angular frequency squared divided by 2 times r squared. And so this will be the radial pressure at this point. And now we need to find, and we know that the vertical pressure is defined as pressure is equal to rho g h. So in this instance, the h will be this distance here, since we're only talking about this section above the depth of the fluid. So we have a pressure on either side of these, and since we know we can only have one singular pressure at this point, we know that the vertical and the radial pressure have to be equal to each other. So we quickly set these equal. We get rho gh is equal to rho omega squared r squared over 2. And very quickly, these rho's cancel, and we're left with h is equal to omega squared r squared over 2g. So now we've derived an expression for the height of this fluid, which will be very important in finding the area or the differential area of the fluid, and in turn finding angular frequency. As you can see, the height of the fluid when it's turning is variable. So we want to know what what the distance is between h naught and the lowest point here. And we will call that some distance d. And what we want to do is we want to derive an expression for that distance d, how much the water has depressed in terms of omega. I'm going to redraw these cylinders. Height of fluid there, and variable height. And as you can see, the volume of these cylinders under the dashed line will be equal to each other. So that means because none of the fluid is filled, the volume above the dashed line also has to be equal to each other. So we're going to set these volumes above the dashed line equal to each other, and from there derive an expression for the depression d. So first, this is just the volume of a basic cylinder, which is pi big R squared because it's the total radius. And this height here will be d. So that makes that very simple. This volume, however, is not so simple. So as you can see, it changes with radius. So what we're going to do is we're going to make a differential area and integrate. So this differential area right here has some thickness dh and some height h. And this will be the same h as we derived in the previous equation. So, looking at this from the top down, this will be the center, and this will be our differential area with some thickness dh. So as you can see, this is just a circle. So we're going to use the circumference of the circle times the height of the fluid to and integrate to find the volume. So it'll be 2 pi r, because it's a variable radius, h d r. And we're going to integrate from 0 to big R. Because we're integrating with respect to r, our lower bounds of integration is going to be the very center, where r is equal to 0, and our upper bound is going to be the very outside, where r is equal to the maximum radius, big R. So, let's separate this a little bit, bring the constants out, and we're going to plug in this h value in here for the height. So that'll leave us with r omega squared, r squared over 2g, and then you can't forget the dr. So from here we see these 2's cancel, these pi's cancel, and now we have some simplifying to do. So that leaves us with r squared times d is equal to, the omega squared can come out because it's not being integrated upon in here, over g times the integral from 0 to r cubed dr. And that's, again, a very simple integral for us to do. And that's what we're left with. And as you can see here, we have an r squared on both sides that can cancel. So that leaves us with r squared left on the right. And now we have a function for the depression of the fluid d in terms of the angular acceleration and the radius, which will be a constant in this case because it's the maximum radius. So we'll write that here in our bank of equations. So now that we've defined equations for both the variable height and the variable depression of the fluid, we can now solve for the angular frequency of the fluid. So first, I'm going to draw yet another cylinder. And we'll say this is h naught, which was the initial height of the fluid before rotation, which means this distance here is d. And so from this picture, we can tell that this distance here will be h naught minus d. And then from before, we know that this variable distance h at the boundary is equal to this h. And at the boundary, this little r will go to big R. So we'll say that's equal to omega squared big R squared over 2g. And so now we just plug these in. We know the total height is equal to h naught minus d plus this h value. So now we just have to substitute and solve. We have h is equal to h naught minus omega squared r squared over 4g plus omega squared r squared over 2g. And so to add these together, we have to get the common denominator. So we have h is equal to h naught minus omega squared r squared over 4g plus 2 omega squared r squared over 4g. And so these cancel, and it leaves us with h is equal to h naught plus omega squared r squared over 4g. And from here, all we have to do is solve for omega, and then we're done. I'm going to bring this out to the side here and rewrite it. And we'll subtract h naught to the other side, h minus h naught. Then we need to multiply by 4g, and divide by r squared. And that'll be equal to omega squared. So omega will be equal to the square root of 4g times h minus h naught all over r squared. And we can take a couple of these out of the radical, which leaves us with omega is equal to 2 over r times the square root of g times the maximum height minus the initial height of the fluid. Thank you for watching this video that I made on Transport 1 materials. Today we covered concentric cylinders, we covered the pressure force that a fluid will exert on a vessel, we covered adiabatic expansions of pockets of air, and we also covered rotation of a cylinder filled with fluid. So I hope you learned as much from this video as I did making it, and I hope to see you next time. Thanks.